Okay, so we are in this book here, Generalized Linear Models with Examples in R. We are in Chapter 1, Question 1.4. Okay, so here's the question. So consider the data plotted in 1.10, okay, and then here's figure 1.10. So the data represents proportion of positive cases for toxoplasmosis plotted against annual rainfall, okay? So notice that the proportion goes between 0 and 1, okay? Right, because it's a fraction. It's maybe there's 100 cases of toxoplasmosis in a population of 1 million or something. It's some fraction, and so the value goes between 0 and 1. And then we have two different models. We have a cubic regression model, and we'll talk about this, and a cubic GLM, all right? Generalized linear model. Okay. So we need to identify some important features of the data and then talk about which systematic component seems to be fitting the data better, and then to explain why. All right. So the important feature of the data here is that it's a proportion. We've already mentioned this. It's a proportion, and it's bounded between 0 and 1. Okay, and so between these two models, the model that is doing best, even though really they both look to be about similarly close to the data, they seem to be both doing a similar job. The answer as to which model is doing best is the cubic GLM, and there's a very important reason that isn't really clear from the pictures here, and that is this. Remember that values for y here can only be between 0 and 1, but if we look at the cubic regression model, the figure is cut off, but we see that the curve is just extending to positive and negative infinity. But these are impossible values for our data here, right? Whereas the cubic GLM is asymptoting as we get to 0 or 1. Okay, so the cubic GLM is doing better here. All right, so that's kind of an answer, but we're asked specifically which systematic component is better, this one or this one, and that's a little bit of a confusing question, because the thing that separates this model from this model is not necessarily the systematic component. Okay, and so to explain that, let's kind of go down here. Okay, so in normal linear regression, in other words, but here we're using a cubic regression, we have this. We have that the expected value of y, or the mean of y, or y without any error, okay, is given by some equation, by the systematic component. Okay, and here we have, so maybe it looks like this here, right? We have x terms up to x cubed, okay? Okay. Well, now what about this? So now here's the, so here's the cubic GLM, and it looks like this. And we see that the systematic component can be identical. The thing that separates the normal regression with the GLM is actually this little guy here, and it's called the link function. Here I'm just leaving it generic because there's a lot of different types of link functions, but for now all that's important to understand is that the link function is transforming the expected value of y to whatever constraints. And here the constraint that the link function is fulfilling is to keep this, to keep the systematic component between 0 and 1. All right, so it's a little bit of a confusing question in that regard. Now, having said that, it is possible to argue that the cubic GLM actually does have a different systematic component. And how? Well, if we just use the inverse of the link function, right, to remove it, well, then we can get that the expected value of y is the inverse link function of the systematic component. And I guess that maybe this right here is a systematic component that differs from here. Okay, that is that.